Hello to first. Now some
Okay, and this. We have to wait a little because the other chairman is not here. Okay, we can start. So this session is what you see, the name there is nanotechnology and IOR, EOR. I'm Jon Otto Fossum, I'm from NTNU, and session chairs, that's me, and Marcio, who's sitting there, and Ying, who's standing there. So this is the list of the talks. It's already in the program, so you've seen this. I marked, there's a color code, so I'm going to talk about these 3 talks a little bit first, and then Ying may say something about this, because I know about this and Ying know about this. So, so this is the plan. So we have a network, Brazil-Norway Nanotech network, which is sort of 14 years old. And this includes all these institutions that you see here, plus some industrial, some of these partners have industrial contacts, and there are other international academic partners in this network. So, we have been existing for 14 years, and this is the result of those 14 years. We have like 31 scientific publications, 134 conference proceedings, 50 invited lectures given in Brazil, 14 workshops in Brazil and Norway. We have educated PhD students. We have had Brazilian Science Without Border PhD students. We have had exchanges of senior scientists, postdocs, master students, and PhD students, both directions over those years. Most of this activity has actually been going on the last 4 to 5 years. This is a list of some of the workshops that we have had recently. The most recent one was in Porto de Galinhas. Then we had one in Rio, we had in Norway last year, and so on. These are some pictures from some of the workshops. This is from a workshop or a school we had in Geilo, Norway, last year, 2015. And these are the participants. There were 21 participants from Brazil. Most of them had never seen snow before, and some of them skied for the first time in their life. And somebody got injured for life, I think. It's actually happened. And this is from in February this year. We had a workshop in Porto de Galinhas in Pernambuco. These are the participants. So in these workshops, we have Brazilian, Norwegian participants, students, and so on, and we have speakers from other countries as well, and some participants from other countries than Norway and Brazil. So what I mentioned, we have published quite a few papers, and now I'm going to mention 2 highlights of papers. Both of them are in Nature, are Nature papers. So we have one last year, together with it's a collaboration between NTNU, IFE, and University of Brasilia, and some other international partners. That's about how you can capture and retain CO2 in clays. And then we have one paper that is coming soon, same journal. This is a collaboration between PUC Rio, University of Sao Paulo, and NTNU. And this one has not come out yet, but it's been accepted. So I'm going to briefly go through those 2 papers. So this is about the capture of CO2 by clays. This is paper. And when we published that, we got in the news, as you see here. So this guy here, his name is Leander. He's Brazilian. He's from Brasilia, and he worked at NTNU. He's the first author on this paper. So what is this about? This is about that clays are decks of cards, and the cards are 1 nanometer thick. And inside this deck of cards, you can actually capture CO2 and store it there for a while and release it in a controlled way. So we in this paper, we study and report the mechanism for that process. This is connected to another project that is going on, where we did not actually publish together with Brazilians yet, but it's coming soon. And that has to do with how we capture and release drug molecules for medical purposes in the same clay systems. So all this is about molecular absorption, capture, and retention in clays. Then the other paper that is coming soon has to do with clay particles also, but this time we study how clay particles absorb on oil drops in water. So we understand, report how what is the mechanism for stabilizing emulsions in this way. by means of adding salt to the water and adding clay particles to the water. And that has clear relevance for increased oil recovery. And that, as I said, is a collaboration between NTNU, PUC-Rio, and University of Sao Paulo. This is a list of the funding we have had for this network so far. The first 10 years of this network had no dedicated funding, but the last 4 years we had these projects, which is CAPES SIU, Research Council Norway, Petromax project, Utforsk project, and we had a CNPQ project that ended last year. All these projects end this year, which means that we need new funding to continue this. And so we have two applications in the system at the moment. One is a Petromax application, which involves these partners, Norway, Brazil, and France. And that is a sort of a continuation of the paper we just recently got accepted, where we studied the mechanism of stabilization of emulsions by means of particles. In this project, we also have some, these partners have direct contact with the industry, just to mention that. Then we have another application, which is an INTPART application for this network, and that application is actually connected directly to this project that we have from the Research Council of Norway in the Nano 2021 program, which is called Graphene Nanoclay Systems. That project has no Brazilian partners in it. That's why we apply for this one, so we can add Brazilian partners to the project. That the Nano 2021 project has these partners: NTNU, IFE, University of Oslo, and University of Manchester. And at University of Manchester, we collaborate with the guy who got the Nobel Prize for graphene, Konstantin Novoselo. He's a partner in this project that we have, which is managed by an NTNU. And now we want to bring Brazilian partners into this. And this project is about actually combining clay nanosheets with graphene sheets in order to make electronic devices. Because that's a fairly new thing, that's actually very new science, is to make electronics from clays. Some groups in the world work on this, and we are one of them. So this is about the manual assembly of clays and graphene, and also about self-assembly of clay and graphene in suspension. This, I think Ying will say something about.
So, maybe as a background, this CNOS collaboration, we have one of the main topics is IOR, right? And we have ambitions to create some joint projects within the topic IOR. I was here for the first time last year to participate in this seminar. In parallel, in Norway, in Stavanger, University of Stavanger and IRIS, and also IFE, we were awarded as the National IOR Center of Norway, working on IOR. And the award was given 2013, and then officially started 2014. So we are about 2-3 years young and old. And the center is awarded 5 years plus 3 years. So after 5 years, you will be evaluated. And if you perform well, according to the criteria, you will be given another 3 years. So totally 8 years, ending 2020, I think. So that's the background. And with this as an anchor point, we want to enhance the collaboration between Norway and Brazil within the topic IOR. So we submitted as a sort of collaborative environment or consortium. We submitted this, what we call IOR NOBRA, targeting 3 main areas, which you can see from the blue boxes. Actually, the first box is management, but the second box is, let me see. I'm sorry, there's a wrong box. Okay, so this is describing the activities. So we want to exchange between the academia and research institute in Norway and Brazil with these activities on workshops and mobility of students and so on. But there is another similar blue box structure which is the target areas. So we are actually targeting 3 main areas with these workshops. One is advanced drilling and well completion technology. The other one is chemical EOR, including CO2 and so on. So this is IOR topics. Third one is environment, how we can perform or increase production in an environmental way. So 3 main topics with the workshops. So you see the partners here is all the partners within this CNUS organizing this on Renobra partners. So it's IRIS, University of Stavanger, it's SINTEF, NTNU, IFE, University of Oslo, and Simula, not Simula, it's a Simula, sorry. And it's Puquirio, UFRG, the Federal University of Rio de Janeiro, and UNICAM. So this is the application we have now in the system to be evaluated. The announcement will be given around end of November, at least within November. And the budget is from next year, 3 years. We only allowed to apply 1.5 million each year. So that's maximum amount, total 4.5 million, and with some kind of internal in-kind contribution. So we have a budget about 6.3 million krona. So these are the budget that can be spent on traveling, staying at the different labs, covering some of the laboratory expenses, but not manpower. So the manpower needs to be covered by the ongoing projects. So that's a mechanism within INTPART. Same with yours. So, so that's about this. But I think it's impressive with this nano network, which has formed a very nice, solid foundation for more applied research to implement some good solutions. So I'm really looking forward. Ideally, I think we should get both. Hope Research Council realize how important these networks are, and we'll see during the November if we get or not. Yes.
Okay, so I also hope we get both. So, because I don't like these 2 projects, this one and no, this one and this one, to be competitors. I think both should be funded, and also this one, of course. So we have 3 projects we want to have money for. So, let me see. So now we can continue with the talks. So the first talk is by Paul Gunnar Dommersnes. Nanofluids for IOR. So then we are going to see how we can apply our nanotech work in IOR. So we combine the things.
Can you hear me? No? Yeah? Okay. So I don't know where, maybe I can stay here. So thank you for the invitation. So I'll just say something about where I'm from first, because today I'm representing NTNU, but I also work in this company, Geomag Technologies, which Arne will give a talk after me. So if I appear in 2 places, this is the explanation. So something about the lab at NTNU. So I'm working with Yanoto, and we've been collaborating for many years now. We work on many things. If you look at this list, this is just some of the things that we're interested in. The sort of basic subject is soft matter and complex fluids. Nanoparticle suspensions, self-organization of particles, nanostructured matter, molecular absorption phenomena, etc. So you would think that this is too much to work on this. And one of the reasons why it works is that in most of these projects, we are working with the same materials. We're working with clay. So that's the sort of philosophy of the lab. So Yanoto talked about this large network in Brazil. So what I'm going to talk about today is the collaboration we had with PUC and USP. So both of the groups are represented here today. So first of all, what is a nanofluid? A nanofluid is simply a suspension of nanoparticles in a fluid, in a liquid. It can be stable or unstable. So this is an example of an extremely stable nanofluid. So it was made by Michael Faraday some 160 years ago. So it's basically gold nanoparticles in a suspension. And you see that it is still stable today. And the Cathedral of Trondheim is also, Nidaros, was also a nanofluid once. It was made of silver and gold nanoparticles. And that's what gives the color of the stained glass. So nanofluid is not a new technology, it's an old technology. And there are many applications. I will not talk about all applications of nanofluids. But there are some, most of you have used it. If you painted at home with water-based paint, you were probably using paint containing nanoparticles of clay, of synthetic clay. And these are particles that we work a lot with. And they are added to tune the viscosity of the fluid. And they are the best solution around today. If you look at nanoparticles in fluids, of course you can have a lot of things happening because the particles interact. So they can be a perfect suspension of particles just floating around like a gas, or they can start to aggregate if you have attractions between the particles. They can form small aggregates, or they can form connected structures like these agglomerates. So that's well known. But if you have an emulsion, if you have something like oil in water, you also have another possibility. That actually the particles absorb on the surface of the droplet. And this is the sort of thing that we are interested in at the moment, how nanoparticles absorb on liquid interfaces. So that will be the sort of main topic of this talk. So first, the title of the talk is Nanofluids for IOR. So I have to say something about IOR. So we are not IOR people. We are physicists interested in nanofluids and things like that. But it's an obvious application is IOR. And IOR, I'm not an expert on all these methods, but there is something common in many of them. Is that you're tuning the viscosity of a fluid, or you're changing the surface tension between liquids. That's common in many of these applications, in some way or another. And nanofluid can do exactly that. It can change the viscosity of the fluid, and it can change the surface, the interface between liquids, between water and oil, for example. And if you look at the list of possibilities, it's, of course, many things that can happen. And when people do IOR experiments in the lab with nanofluids, it works. But even in a sort of controlled setting, you don't know exactly why it works. And there are many models or many thoughts around, but nobody really understands this. And one of the things that has been sort of popular is this Vasan model, where you say that actually the nanoparticles somehow lifts off the oil droplet from the surface. And another possibility, of course, if you have nanoparticles, they will clog the porous medium, and that will change the flow in the porous medium. Another possibility is that it works in a more classical way, a little bit like polymers. that it changes, it makes the fluid viscoelastic. We have been more interested in this, this possibility, that particles absorb on the surface of the droplet, and that changes completely the flow of the oil-water emulsion. And this is not a new concept in a way. It's actually, it's been known for 100 years that you can stabilize emulsions with particles, with small particles. And in Norway, we drink every day this kind of emulsion, because milk is a particle-stabilized emulsion, stabilized by protein particles. So it works with basically any kind of particle. If you add, it doesn't have to be a hydrophilic or hydrophobic particle. Any particle likes to sit at the interface between two liquids. And you can prove this rigorously, that it will always gain energy by sitting at the interface. It will always gain capillary energy, simply by wetting. And as you look at this, particles that are more than 10 nanometer, it will always be larger than the thermal energy. So that means that any particle, say, in the range from 20 nanometer to several microns, once it gets at the interface, it's completely stuck. It will not move away from the interface. So that's a very strong mechanism for changing the rheological properties of these emulsions. There's another thing which is sort of becoming more relevant now, that you can also use what is called Janus particles, particles that have different wetting properties or different electric properties that are not uniform. These particles are even better to stabilize emulsions. And so it's sometimes called Janus beads, because you can have a particle with different properties on each side. And these particles generically likes to even better to sit at the interface of liquids. And clay is actually a very good example of such a patchy or Janus particle, because it has a different structure on the edge and, compared to the surface. So it will have some additional features when it absorbs at the interface. I will not talk about this, I just mentioned this now. So these are some of the publications not all the publications, but some of the publications that we had the last years on this subject. And I will talk about the most recent ones today. When we study these droplets or emulsions, we actually do it in a way which I think nobody else does in the world, because we don't use conventional rheometers. Well, we use them, but that's not our main focus. We try to develop other methods, new methods to sort of characterize and understand droplets and rheology of droplets. And it's actually based mostly on, most of the time, on electric field-driven flow. So this is a way to create flow on small scales. And I will show you how this works. So this is electric field-induced flow in a half millimeter size droplet. And it contains clay on the inside. It's an oil drop that contains clay. And you see that in about a minute, this flow transports the clay particles to the surface of the droplet. And once it's on the surface of the droplet, it sits there, so it doesn't escape. So this is a small, low concentration, so it only partially covers the droplet. I will not explain this also in detail, but as I said, it's an electric field-driven flow. So it's an electrohydrodynamic flow. So there's no direct forces on the particles themselves. They're just convected by the hydrodynamic flow. This is very similar to what you would have if you had droplets going in a porous medium. You will also have these circulation flows. So this is sort of emulating what is happening in a porous medium. We can also use electric fields to study the coverage of droplets, because the coverage of droplets is not easy to see if a droplet is covered or not. And this is an example of a droplet that is fully covered. So now the two droplets here cannot coalesce. The first one, it actually has some opening in it. There are some holes where the liquids can connect, and once they connect, the capillary forces makes this the droplets coalesce. So what is happening here is that we will do this in different ways. You can do it by electrodynamic flow, which sort of pushes the drops together, or it can also be more conventional electrocoalescence. We're also using the same methods to characterize the elasticity of droplets. So this is now not clay. It's actually a droplet covered by colored beads, micron-sized colored beads. But you can see it now that it actually is an elastic interface, and it has a yield stress, has a yield electric stress. So once you get beyond this, then you see deformation. But and you can also see a viscoelastic relaxation. So there's a lot of interesting properties on the rheology, which is not the rheology of the bulk fluid, but it's the rheology of this surface layer of particles. So you have a two-dimensional rheology, which sort of governs the shape of the droplet and the mechanical rheological properties of the droplet. This then now is a clay droplet, and you see a similar yield phenomena. That actually this layer resists for some time, but when the force gets above a certain critical field, then you see deformation. Okay. This is another example where you see crumpling of, you really see buckling of the surface layer. So you really see that it is elastic. And this is a completely sort of generic, it happens with all kinds of particles. If you just have full coverage of particles on the surface of the droplet, you will see this, and you can measure the mechanical rheological properties of this droplet. Okay, so these are just the different particles, but you see that's a very similar phenomenon. This also happens with clay and happens with nanoparticles. It's a completely generic phenomenon for these particle-covered droplets. So they are not fluid; they are elastic. And this, of course, you have to take into account if you make a model or if you want to understand what goes in a reservoir where you have small particles. And that's our focus. We also show that there is actually can be a transition in the flow dynamics of such droplets, which resembles what you see in red blood cells in the body. You can actually see a transition from a capsule that is behaving, or a particle interface which is behaving like a solid, and it can go from a solid to a liquid interface. And then you see this tank treading dynamic, which is the same, very, very similar to what you see in red blood cells in shear flow. So of course this, you also have to take into account if you think about the flow of particle-covered droplets in a reservoir. So these are sort of generic mechanisms. And we have developed new methods to actually image these transitions, these rheological transitions of this surface layer. So this is a droplet which has been covered by exactly the same particles, but with different colors on each side. So we have a method for creating such particle-covered droplets. And you see that when you are at low shear, then there's a partial mixing of the layers, but eventually this layer becomes completely fluid. Okay. So this sort of confirms this transition. Okay. So this is one of the things that we've been working a lot on now for several years in collaboration with Marcio Carvalho and Courtier Araki, Puki and Espi. And it sort of concerns the same thing. We're looking at the elastic properties, the rheological properties of these particle-covered droplets. But now we are looking with nanoparticles, and we cannot really image what is going on directly in the microscope. So you need to look at this in a different way. And one way that Marcio and his postdoc looked at was the mechanical properties of such clay nanoparticle-covered droplets. So this is using pen and drop method and sort of standardized methods for measuring viscosity and elastic properties of droplets. And what they see is very interesting, that you can have, again, a kind of transition. If so this is the elastic modulus of the droplets for different clay concentrations. And you see that you need a certain amount of nanoparticles for this layer to become elastic. So this was sort of the starting point for trying to understand what was going on in this system, because we also saw that it was highly dependent on the salt. So if you have low salt or high salt, the system behaved very differently. The elasticity of these capsules are completely different. And sort of important breakthrough in this project was the collaboration with Koiti at Araketi at USP, where they have this Raman confocal microscopy, where you can image the droplet in 3 dimensions with submicron resolution. So you don't actually see the nanoparticles, but you start to see small aggregates of nanoparticles. And you can actually see what's going on at interface. And the sort of conclusion of this project was that it turned into a real discovery, because it's been known for a long time that when you have nanofluids, if you have particles in a suspension, there are sort of 2 generic systems. You can have a repulsive crystal of glass of these particles, or you can have an attractive a gel. But nobody showed previously that actually you can have the same thing on the surface of the droplet. So you can have actually, what happens in the system is that depending on the salt concentration and on the nanoparticle concentration, you will have 2 completely different surface structures on the droplet. So this, either you have a sort of dilute crystal on the surface, or you have a gel on the surface. So this has not been accepted in scientific reports by Nature, and will soon be published. Okay. So how much time do I have? I almost finished. 2 minutes, okay. So I think Jonathan already talked about this first application, Petromax 2. So what we're hoping now is that we will get this, and so that we can continue this project, because it has a very good starting point, I would say. So I think we have sort of laid the foundation for doing this project. So it's called Nanofluids for IOR and Tracer Technology. So it's in collaboration with many partners. But I also would like to see this project funded, because this is also something that we're very interested in. And Jonathan talked a little bit about this. He mentioned the interaction between clay and graphene. And it's very interesting that graphene and clay are in a way very similar. It's not a molecular layer clay, but almost. It's also, you know, that graphene is made of graphite. It's derived from graphite, which is a stack of graphene. And clay is exactly the same thing. It's a stack of thinner lamellars, which are a few nanometers thick. And it's already been shown by Jonathan and Novoselic that they actually interact, and they form heterostructures. What we want to do now is to look at this in fluids. So this is also a nanofluid. It's also when you exfoliate clay or graphene in a solution, it's also a nanofluid. And we want to look at the assembly in this system. Okay, so thank you for your attention. Any questions, or should I just go for the next speaker?
Okay. Okay, is this on? Okay, the next talk is actually the speaker is not here. It's a recorded talk. So we'll hear the sound and the PowerPoint will run by itself. So let's see if that works. This will just start.
Hello to everybody. The subject of the presentation is touching on the possible future use of nanoparticle. Hello to
the sound
everybody.
Will appear soon, I hope.
The subject of the presentation is touching on the possible future use of nanoparticle-based tracers in the petroleum industry, but this time just limited to application in single-well push and pull operations. Firstly, a brief repetition of this technology. Measurements of residual oil saturation, SOR, can be performed in a defined volume around a single well, most frequently an injection well, by so-called push and pull operations. The probe volume corresponds normally to the distance of some 5 to 10 meters from the wellbore. Question: how can we measure residual oil saturation in a watered-out reservoir section with tracers? The answer is the simultaneous application of passive water tracers and water oil. Now some basic information. A passive water tracer moves only with the water flow. A phase partitioning tracer distributes between water and oil. At residual oil saturation, water moves, but the oil is stagnant or close to stagnant. Here a beaker, we see a beaker with an appropriate type of injection formation water and a corresponding amount of equally appropriate oil. We have dissolved the passive tracer and the phase partitioning tracer in the water. Then we shake until equilibrium has been attained. The result is that the passive water tracer remains in the aqueous phase while the partitioning tracer distributes between phases in a certain ratio, depending on the molecular properties of the partitioning tracer and other factors. By analyzing the tracer concentration in both phases, we can determine a constant, which we call the partition coefficient, or, if you like, the distribution ratio. The knowledge of this K value is imperative for SOR determination. A simple animated cartoon illustrates the principle for SOR determination. Here we have a cartoonic reservoir rock with sand grains, porosity, permeability, and a residual oil saturation on the surface of the sand grains. Injection of a passive tracer follows exclusively the water flow and is insensitive to the residual oil saturation. Simultaneous injection of a passive and a partitioning tracer is illustrated here. The partitioning tracer likes to spend parts of its time in the stagnant oil layer, meaning that it is lagged behind the passive tracer, that is, produced at a later stage. The time distance between their production is proportional to the water contactable residual oil saturation. This is the simplest formula to calculate the water contactable residual oil, and we see that the K value is included in this formula. I will not explain this formula further here. What happens if we co-inject a passive and a partitioning tracer into a certain depth from the wellbore, that's the push, and then start to produce these back, that is the pull? A slug of passive and partitioning tracer followed by larger volumes of non-traced water result in a positioning of the passive tracer like a donut around the wellbore at a distance which is larger than the donut formed by the partitioning tracer. That is, they separate on their way out into the reservoir. On back production, the passive water tracer will move faster than the partitioning tracer, and they will be produced simultaneously. Hence, there is in principle no difference in the production curves of the two tracers, a difference which is a requirement for the method to work. The single well push and pull method is based on injection of a water oil partitioning and a hydrolyzable ester in and in situ generation of a passive water tracer according to the following reaction. Ester reacts with water to produce alcohol and acid. Here the produced alcohol is a passive water tracer. Therefore, injection of a primary reacting hydrolyzing tracer is necessary. The positioning of the partitioning tracer injected as a pulse is illustrated by the green dots. A passive water tracer, which we can call a cover tracer, has been mixed homogeneously in the whole injection volume, including the volume of the partitioning pulse. The positioning of the front of the cover tracer is shown by the yellow dot. After the injection, the well is shut in for a few days until approximately 50% of the injected ester has converted into alcohol and acid. On back production, the remaining partitioning tracer, the ester, and the generated passive water tracer, the alcohol, start on the same starting line. They separate on their way back. The separation is proportional to residual oil saturation. Here are the resulting production curves. The distance between the first movements of the alcohol curve, which is the passive tracer, and the ester curve, which is the partitioning tracer, is shown here. The traditional single well method, which was developed by Harry Deans at Exxon at that time in the mid-70s, and which is still in use, suffers from a number of weaknesses. The most serious is the large amount or large volume of ester solution required, which might be hundreds of barrels. The challenge, this challenged the conservation of the original conditions in the near-well area. In addition, the fact that the hydrolysis rate of the ester is catalyzed by both acid and base will change the hydrolysis rate during the reaction period because of production of a large amount of acid. If this cannot be taken care of by the corresponding large buffer capacity of the reservoir water or the reservoir rock, we are working on improvement of the single well method in several steps. The first is to develop new esters with much higher sensitivity, implying that only small amounts of tracer compounds are necessary. This will take care of the worries expressed above. Some of the new esters are based on molecular complexation of lanthanide ions with so-called chelate formers. These are carboxylic acids with several carboxylic groups. The ester is formed by reacting the metal complex with an appropriate alcohol. The new esters are then analyzed with laser-induced fluorescence spectroscopy, which is a very sensitive analytical method. The different rare earth metals fluoresce with different colors, and different complexes show difference in decay time of the fluorescence. And we exploit this by time-resolved fluorescence spectroscopy. So far, I have not mentioned nanoparticles at all. However, we are now working on the possible use of functionalized nanoparticles for such tasks just described in order to overcome some remaining challenges. reduce time for single well push and pull operation, and to reduce operational cost. Here is where nanoparticles come into play. At present, we are interested in nanoparticles as a transportation medium. Here is, for instance, a dendrimer with internal porosity capable of including various types of tracer compounds. These tracer compounds may be released with an external triggering mechanism. Principles and examples is given over the next few picture frames. The principle is as follows. The functionalized and partly lipophilic nanoparticles carrying passive and partitioning tracers are injected to an estimated depth. The speed is slower than for the water itself. The particles are slowed down due to chromatographic interaction with the remaining oil. The particle is chased by an engineered fluid which contains the triggering mechanism for the release of the tracer. The speed of this liquid is close to the speed of water, and at a point the particle is overrun by the liquid and the tracers are released from the particle. The passive and the phase partitioning tracers with no start at the same starting line at some distance from the wellbore are produced back and they separate as described previously. With this method, no shut-in time is required and there is no ambiguity due to reaction of an ester during injection and production. Is this mechanism just a fairy tale? This picture is a cartoon of the engineered nanoparticle, which may be a dendrimer or a silica-based particle with or without a solid core. Tracers are enclosed in voids in the nanoparticle. There is a locking mechanism, a valve, here illustrated with a rod and a ring, which prevents the tracer molecules from escaping. A molecular example of such a rod, which is covalently bound to the nanoparticle, is given here. One key element is the positively charged amine group. This is a molecular example of a ring, a cyclic complexing agent containing a number of oxygen atoms which have a delta negative charge in the molecule. This ring will bind to the positive amine group in the rod. Nanovalve can be opened in this case by change in pH. That is, the chasing liquid contains a base in the present example. The base will remove one hydrogen molecule from the amine group and thereby the charge. This implies that there is no reason for the ring anymore to be bound to the rod and the tracers are released. The valve may also be opened by influence of an electrolyte containing a salt of a cation which has higher affinity to the ring molecule than the rod has. The result is that the cationic molecule steals the ring by complexation and the tracers are released. Examples of such cations are given here. And examples of tracer molecules may be fluorophores like coumarine, fluorescein, rhodamine, or rare earth complexes of various kinds, and others. This is the final picture frame. Let this cube represent in a relative way the original amount of tracer needed for the single well method developed by Exxon with a corresponding relative timeline. The method improvement will proceed in sequential steps where this method is under development at IFE in a project under the National Norwegian IOR Center, illustrating the reduction in tracer volume needed and a somewhat reduced timeline. Introduction of nanoparticles will further reduce this volume, but in particular reduce the time needed for field application. Finally, we are working on technology which enables will enable estimates of the level of residual oil saturation of a particular reservoir already during drilling. Complexation and installation of a new well. That is, before any production start in a so-called micro sweat. Here we have the possibility to check the efficiency of various IOR methods as well, also upfront production start. But this may be the subject for another presentation in the future. Thank you for listening.
So, it works, yeah. Good. So, Koiti is next. I don't know. I will ask him later.
Thank you. Hello. Thank you very much. First of all, I would like to thank John Otto for inviting me for this meeting. Not only for this, but inviting me for joining this fantastic network that we started collaborating about 2 or 3 years ago, from 2 or 3 years ago. So I will also thank Paul that made a very nice introduction, so I will go directly. And I will change the point of view for the chemistry point of view. So we are working on trying to develop nanoparticles technology. So I will try to explain what it is. But first of all, I would like to show you from where I'm from. I'm from University of São Paulo. This is a photo of the main campus. And all these projects start with the challenge of Petrobras that propose the following question: how to use nanotechnology for in the oil industry. So this was the challenge that was made about 8 years ago, and since then we start to look at what we could do. So what we realized is that if we were able to control the properties of nanoparticles, we will be able to develop application not only for oil industry, but for many other applications. And when we look at the possibilities of how to doing that, we faced many different preparation methods. So from the conventional pyrolysis or physical methods, sonochemical methods, microemulsion, thermal decomposition, co-precipitation, hydrothermal processing, and so on. But in order to try to use those nanoparticles for, say, enhanced oil recovery or something like that, the main target was producing nanoparticles that was completely dispersible in a media, and also that should be able to enter the smallest pore, say, of about 10 nanometers. So that was the main challenge. And when we start to look at the preparation methods for nanoparticles, the main problem was that, okay, we can produce the nanoparticles, but generally they start to agglomerate, and these agglomerates are very, very hard to disperse. So we should develop something that allows us to produce dispersible nanoparticles, not in lab scale, because what Petrobras wants was something like tons at once. So, and what the methods we had at that time could do is some grams at most. So this was the main challenge that we were facing. And since then, we tested many of these, actually almost the three of the top, the last one. The pyrolysis method we knew that didn't work very well because we have commercial nanoparticles and they have that properties of agglomerating very strongly, and which was very, very difficult to disperse. So what we developed in this period of about 8 years is a method that allows us to prepare the central core of the nanoparticle in a reproducible way. Say we can produce this with about 7, 8 nanometers diameter, and also we are developing all the chemistry, or the surface chemistry, to put whatever we want on the surface. Of course, this whatever is too much, but we can put a lot of different molecules on the surface. We can put things like this with amine groups, like this with carboxylate groups. This is sugar, aliphatic chains. This is oleic acid, and even biomolecules on the surface. So this is a way, actually, as said before in the previous presentation, is a nice way to control the properties of those nanoparticles, how it will interact, and if you want to look at how it interacts with oil and water, controlling this surface is the way to do that. So what we can do right now. It was developed a method, for example, to prepare titanium dioxide nanoparticles. This is a 5% in mass dispersion. So you can see that despite all the properties of titanium dioxide, you can see through it, it's completely clean, showing that there is no large aggregate or something like that. And the nanoparticles is about 8 nanometers large. We have nice size distribution, and we can produce in a crystalline form in, say, about half a kilo a day in our lab. So this is what we can do right now. And also, it was developed a method for iron oxide nanoparticles. In this case also we have similar properties. This is the dynamic light scattering size distribution. So we have a size a little bit larger than what we can measure directly from, for example, TEM images. But those nanoparticles also are highly crystalline, and we have a high magnetization, and it's possible to disperse completely in solution. Those dispersions you can see in here. This is a sample that was prepared at once. It's a half a kilo of a solid nanoparticle made of iron oxide. This is actually silver metal, okay? And it's a solid also. And it's possible to disperse like this. You just add in a solvent, and it completely disperses, and you can measure the dynamic light scattering. You find the nice size distribution. In here, you have this iron oxide, this magnetite, and you can do similar thing. And another very important aspect on those nanoparticles is that we have no excess of surfactants or other things. We just have the core and the functionalizing layer, and this gives this kind of material is a solid and completely dispersible one. These solvents are hexane or toluene, is an organic solvent, but we also have nanoparticles with similar characteristics that are dispersible, for example, in water. We are also working with nickel hydroxide, with I showed silver metal, graphene oxide, and this possibility of dispersing very easily, completely, those nanoparticles allows us to interact them very nicely with other materials generating nanocomposites. So I will show you later one result. Well, this kind of nanoparticle actually can be very useful in nanomedicine, because in nanomedicine you want actually completely dispersible nanoparticles and completely pure nanoparticles, because anything that is free in solution can cause actually side effects. So and also it's necessary to do a very how to say, nice engineering, molecular engineering at the surface, because if not, actually the molecules are not active. So for example, in case of antibodies, you should bind to this Fc portion. If not, it's not active. So I'm just showing this to stress the fact that nanoparticles can be tailored in a proper way. Those are the dynamic light scattering results of modified functionalized nanoparticles. The IR showing that everything is perfect. All molecules are bound at the surface. And we tested, for example, as a contrast, MRI contrast agent. And this relaxivity actually shows you the sensitivity of those nanoparticles for that technique. So because of the larger magnetization of the nanoparticles, those are more sensitive as contrast for MRI. Well, as I told you, if we can prepare those fully dispersible nanoparticles, it's possible to prepare nanocomposites. For example, nanocomposites joining two or more materials that allows us to prepare nice materials for removal and concentration, actually, of pollutants. You can actually concentrate and remove metal ions, organic molecules, dyes, this kind of thing. This is a video showing this is a conventional material. This is our material. And you can see that the dispersibility in water is higher. So the idea here is to treat very large volumes, just distributing this material and then recovering, as I will show you. Okay? So here you have a dye, and soluble materials are quite difficult to remove from water. So just interact for, say, a few seconds. And then, in this case, these nanoparticles, this material contain actually magnetite nanoparticles. So it's possible to separate them very easily. And then it's possible to recover what is this is concentrated here just using a solvent or using different kind of techniques as shown in previous presentation. So this kind of material we are trying to produce, going to the pilot production in order to make this available for further development. So in this case, simply adding acetone, you can remove 100% of what is adsorbing. And in the case of metal ions, for example, this is an experiment that was made with wastewater containing mercury. And it's possible to remove completely this mercury below 13 ppb, just using this material. Okay? Other metal ions are also possible. Going back, those developments also were made with Petrobras that was interested in spills and this kind of things. In the case of oil exploration, this was shown before by Paul, and our targets, one of our targets was this wedging effect, say, that we don't know if it's true or not, okay? The effect, if the mechanism is really like that, it's not clear defined yet. But when you use nanoparticles dispersible in water and use in an experiment using, for example, an enamel cell to see the effect on how it influences the release of oil, what we got is this. This is just water. This is water with nanoparticles. Okay, you can see that the rate of removal, of recovery of oil increase. Also, the amount is increased. So we don't know if this effect is true or not, but it does have a positive effect on the removal of oil from the porous media that is in here. So is this kind of work that we are doing. We also tested this for to change the viscosity of polymer formulations, and it's worked very, very nicely with about 0.01%. It's possible to have a very significant effect. There are other properties that we also tested. Well, what we are trying to do is more or less follow this planning. We are trying to prepare nanoparticles that are completely dispersible and with engineered surface in order to try applications in different fields like sensor and devices, environmental, petroleum, and oil. That is the main for us. Lubricants, smart fluids, and also in nanomedicine. Of course, this is possible only with fundings and collaboration of many people. Here, I must add, of course, NTNU and PUC-RIO. Sorry, I forgot that. And I would like to thank everybody. Thank you very much for your kind attention.
Okay, thank you. And then the next talk is by Caetano.
Oh, here? Tem outro microfone aqui, só.
Well, can you hear me? Well, first of all, I'd like to thank you the invitation. This is a double thanks. First, to give a talk at the CBPF for a physicist is a kind of very important place for us in Brazil. And second, to tell about the work that we are doing at the University of São Paulo. I have to make a correction in the program. I'm not that so ambitious to say that we are going to the macro scale, but in this talk, we're going to stick it until the micro scale, and somehow you can talk later how to do the bridge between the micro and the micro and the macro. So this is a work that is done at the USP, University of São Paulo, with support of Petrobras, and done in our group, the NanoPetro. The idea is to use nanotechnology in order to be used in the oil and gas industry. Now, the problem that has been posed to us for the industry was a little bit different from what Coach have mentioned. The problem was, are you able to double the production of oil based on nanotechnology, for instance? Or you can use some ideas in order to try to go beyond the average production that you have it. And to go that, to really try to see if you are able to double this production, you have to better understand what is going on in the interface between the rock, the oil, and the brine, for instance. And the way that I'm going to use nano here was to try to control this interface. And you can control this interface in several parts. The first one is to use nanoparticles, Coach have mentioned before, in order to try to see the interface between the brine and the oil, with the rock. And they're going to drive the oil now based on the surface change. So you're going to use the nanoparticle as a way to change the interfaces. The second point of view that you may think to use a nano is that some part of the oil, it may be trapped in the nanospores media. So then the idea is to propose what we are calling nano IOR. We are going to inject water or brine in order to displace oil, if you have oil there, in the nanoporous space. And the idea is to try to see what is going on in the sense that you're going to use pressure in order to drive the displacement of oil. As well, nano appears in the industry in a very, I would say, bad way. That is, you have the aggregation of complex matter, the so-called phosphatins. In the disaggregation, it happens in a very, at a nanoscale. So if you understand what is going on at this scale, then you can propose ways in order to control either the aggregation of phosphatins as well to try to see if you are able to recover more oil out using nanotechnology. Now, the idea that we're going to propose here is the so-called digital oil, where you're going to try to predict the oil and gas behavior at reservoir conditions. And they're going to do that using a set of computational approach, of course, together with some experiments. And if you see in terms of time and space, usually in the industry, if you are thinking in terms of the properties of the oil, you want to know what is going on with the formation water, with the oil, of course, the gas, CO2, kerosene, asphaltenes, the surfaces that you have it, and also the chemical additives that you have it in the system. And this is mainly what the people do in the industry, in the petroleum engineers. It's more what is called digital reservoir. The question is how the properties of those complex systems can be used here, how to get this information. And the one way to get this information, that is actually what you're approaching, is using molecular modeling, where you're going to use quantum mechanics and also molecular dynamics in order to determine the thermodynamic properties of those systems in this way to describe the oil in a molecular model. Now, this is not enough to make the conversation with the digital part, or the digital reservoir, because the properties that you are interested in there is mainly the surface tension, the densities, and the viscosities. And the way to do this bridge is computationally, it can be used the so-called method of Letts-Boltzmann, and as well some experimental high pressure, high temperature, where you're going to obtain the hydrodynamic properties of those systems. And you're going to do the conversation in such a way that the information that comes from this scale are going to be used as an input for this scale here. At the same time, all the information for the thermodynamics and the hydrodynamics now can be used in the reservoir simulation. And so this is a situation where you can actually probe several scenarios of cases where you can choose or tune what chemical additive you'd like to have it prior the testing experiments or in a plant. So you can really searching for the best options for a given reservoir conditions in the chemistry that you have it in the system. Now, since the idea here is mainly like to take care about the health of oil reservoirs, I think in the lunch yesterday we have discussed about that. Mainly, you want to know how much oil you can take out, and you're going to use either the EOR, the nano EOR, nanoparticles, or nano IOR. You're going to try to displace oil that is trapped in the non-porous media. At the same time, you want to take care about another problem, that is the accumulation of asphaltenes, and you want to know how these asphaltenes aggregate and how to control this aggregation of those systems. So the approach that you do, since you are in the physics institute, is really going in a multi-scale approach. We are going to go from quantum mechanics in order to try to solve the so-called Schrödinger equation, in order to understand the interaction of these molecules with the surface. And this information now are going to be used in another level. Note that here you're already in the nanoscale level, where you can obtain the thermodynamics and kinetic properties of those systems. Now, these properties are going to be used in the kinetic theory, where you're going to really go from very fundamental point from the quantum mechanics, understand the forces and the interactions that you have in the system, in order to characterize bimolecular dynamics, the thermodynamics and kinetics of kinetics that you have it, and finally try to make the bridge where you can go for the micro scale of the porous media. Now, then this is done in such a way that you are not put any experimental information ahead. You can compare with the experiments, but you can, by first principles I mean for quantum mechanics, you're really going to try to understand what is going on the system. Now, last year I had also the opportunity to give a talk in this conference. I'm going to give to you an update what you have done so far. Now, the first point that I think that was quite interesting is that you could learn more about the asphaltene nanoaggregation by using quantum mechanics. And the idea here is that you learn how these asphaltene and resin molecules behave from the quantum mechanics point of view, and you can understand what is going on with the electrons mainly. So you have a higher density close to the core of the dimers, for instance, and when you increase even further the size of the asphaltenes, this charge is more displaced. So now it's more difficult to get more molecules come to close to this situation here. At the same time, you have a difference in the dipole moment of the molecule. So as you increase the molecule, you have a certain limit of size that you can reach on this system. And you also learn how these asphaltene molecules can be adsorbed on calcite. That is, for us, is quite interesting for the carbonate interaction. And you can learn that, firstly, you have a preference for the calcite, the asphaltene resin to non-aggregate, then to be deposited on the calcite. Now, what you can learn from here is mainly how is the forces and the energies of interaction between the molecules and the surface. But this is still quite far from the reservoir. But based on this information, what you have done was create some oil and brine models. So it's given a composition. You can displace, now that you understand how is the interaction of these molecules, you can derive these interactions. you can characterize this oil in terms of the viscosity, the density, the surface tension, and so on. At the same time, you can see what happens when you have an interface with the brine, for instance. And here you have a profile of the density where you learn what is the preferential positions that you could have your molecules near the interface. And this is what actually is the part that tells to you how is the interface tension that you have there. At the same time, the density. Now, with this information, what you want to do, as I mentioned to you, is to control the interfaces in the flow. And it has been already mentioned here that mainly what we want to try is to control the viscosity and the surface tension. And we're going to try to do it in 3 ways. The first one is the so-called nano-EOR. You're going to control the chemical environment. And you're going to do that by functionalized nanoparticles and surfactants. So this will be wettability modifiers. So you have a surface driving flow in this case. The second part, the second proposition is the so-called nano-IOR, where you're going to control the confinement of these fluids in nanoporous media and try to displace this oil that may be trapped there. And finally, the so-called low salinity EOR. I didn't hear so much on this workshop about that, but mainly there are several things that the Norway have explored. That is to control the electrostatic environment, the so-called the smart water. So this will be an electrokinetic driving flow. Now, for the nano-EOR, so you're going to design nanoparticles and try to see how much oil you can displace by injecting these nanoparticles. And the first problem is to try to see if you functionalize, for instance, a given nanoparticle, how this nanoparticle is going to interact with the oil, with the water, or brine, and also with the surface. And here you choose a clay. Notice it has been given to us as a proposition. And you learn how is by first principle calculations, you learn how is the force with respect to the distance, mean the interaction of this group, functional group, with that surface. How much is this force with respect to the different kinds of functional groups that you can have it there. So you could explore hydrophobic and hydrophilic functional groups. And based on this information, you can derive how the molecules interact with each other. Finally, you can put this nanoparticle now that you learn how it interacts with the rock, with the brine, and with the oil. And here I have to thank you about you guys, because last year I have been, by seeing the seminars here, we thought that maybe to simulate magnetic systems would be possible. This is something that we are doing right now. You should try to get the information at molecular level, what is going on, to model also the behavior with a magnetic field in the molecular dynamics. Now, what you can learn for these calculations. You can do something that usually in the lab it can take a long time, and here is done in a short term. And you can learn how is the interface tension with respect for a given concentration of salt for different nanoparticles, hydroxylated, hydrophobic, or hydrophilic. You can also learn how is the contact angle with respect to the temperature, pressure, and here the concentration of salt. And as well, you can learn about the viscosity. So you have all the ingredients that comes from molecular dynamics where the potential, the energies and the forces has been derived by quantum mechanics. Now, you will learn how is the behavior in terms of the thermodynamics, but still you need to know how effective will be this nanoparticle in order to displace the oil. Now, the way that you do that is try to go beyond the so-called molecular dynamics, where you have a limitation in terms of nanometers and nanoseconds. You're going to use the Letts-Boltzmann method, where you're going to try to map these physical properties that you have obtained by molecular dynamics, density, viscosity, and surface tension, the contact angle, without and with the nanoparticle. You already see that the inclusion of the nanoparticle decreases the surface tension, At the same time, you have a change in the contact angle. And then you can map this information in the so-called parameters that you have it in the Let's Boltzmann that mainly tell you how is the fluid-fluid interaction, the fluid, the rock, and the viscosity and the densities. And with this information, then now you can play what you have in geometries at a micro scale. This is more or less what happens. So you can take a microphotography of a porous media. You create a computational rock model about that. And here you have an injection of a fluid, have nanoparticles, where the thermodynamics and the kinetic properties of those fluids is embedded on the red fluid here. And you do see how much oil has been displaced. And here you have several situations like this dead end part here or this to see how much oil can displace. In the compared with what I have presented last year, what you have done in terms of methodology is to change everything in such a way that you can have a re-injection of the same fluid. So you have a second injection, and then you do see how much oil has been displaced in the system. So even with the second injection, there are some part of the oil that remains trapped on those systems. So you're not able to take out everything. So as a summary, then you start with a condition that you are fully saturated with oil. In the first injection, you are able to displace part of this oil. In the second injection, you can somehow increase even further this displacement. And this can summarize in the curves that it can help us to design nanoparticles or solutions that can be used in order to displace. So here you have the saturation with respect to the time. Note that the scale here is already in terms of seconds, where the information that had been obtained from molecular dynamics was at nanosecond scale. So you really take from the, going in terms of scales, going from the nano to the micro scale in this particular case. And you see the evolution of either the brine and the oil that has been displaced for each of the parts, and how much oil has been displaced with the different injections that you have in the system. And with this, you can map and try to figure out what will be the best options in terms of the nanoparticles or the dispersion that you want to use it for a given geology of a given situation that you have it here in the system. So I have to tell that also the conditions here is conditions that you have in the reservoirs, so high temperature, high pressure. And you know this information because you have done the molecular dynamics part. So nowadays, we still probing, you have a database where you try to explore the best options in terms of nanoparticles in order to displace the oil, also to see how much all the nanoparticles, the surfactants that can be used in order to really do a nano-EOR in this particular situation. So, but this, of course, is as a computational model that every time you have to benchmark with some experiments and try to understand what is going on this injection. Now, the second part of this talk, this is the so-called nano-IOR, where you're going to displace the oil that will be trapped in the nanosporous media. And this is a situation that either one of the questions is if you have oil inside of these nanopores, and you have answered this question by doing the molecular dynamics calculations, where you really do see that spontaneously the oil can penetrate in these nanopores, as well the water or the brine can penetrate on these nanopores. And also you have discovered that you needed to have a first form, in the terms of geology, you usually have a thin layer of water, this may be possible to displace the oil that has been trapped on the nanoporous medium. But this has been something that you have presented last year. But one thing that is important in terms of confinement and I think you really, this methodology can really help us, is to either understand what is going on in terms of the surface, the interaction of the brine or the oil or with a given surface, in this case is the calcite. And here the idea to explore and to try to understand what is going on nearby the surface. Why this is important? Because with molecular dynamics, you see the dynamics of the molecules close to that surface, you learn how is the structuring, for instance, of the water nearby the interface. And this tells us until which regime, until which distance the nano is important. I mean, the interface is important. In particular here, the case of the calcite, you learn that you have a very specific layering of the water near the surface, and you can calculate the diffusion for each distance of your slit, the distance between the two plates of the calcite for your porous media. And you do see that as you increase the slit size, of course, you can reach what you have in the bulk water. But the interesting thing is what is going on in a very nanoscale part. I mean, this is 1 nanometer, just nanopores. And particularly here, you have the water, whatever size that you have it in these nanopores, you have a very low diffusion of the water. And you know from molecular dynamics what is going on there. And this is a kind of important information that if you want to explore or play with the interface between the water and the brine and the oil, this is the region that you have really to act. Because here's where you're going to have a displacement of the oil near that interface. It's not only that. This morning we visit here the lab on the NMR. And with molecular dynamics, you are able, for instance, when you do the experiment for NMR, when you have a fluid confinement, you can have this fluid in several scales or several parts of the system. And in the end, what you have is this. Is basically your spectra that you are not able to distinguish between the microporous, the macro, and the nanoporous media. And with the molecular dynamics, you can monitor what is going on in each of these parts on the systems. And you can here estimate it with the so-called T2, the relaxation time with the NMR. And here you see how is T2 change with respect to the size of the distance with respect to the surface, I mean the size of your slit. And you see that the response on the surface is very much different for the response that you have in the bulk phase. So then you are able to assign which is the peak for which part of the system that can be helpful for the experimentalist, for instance, in order to assign what they have it in their spectrum. And not only that, you also can have a so-called Google's view of it, because you can learn how the water is displaced or how the water is structured near that surface. That is something that is important, mainly for the smart water, because what you want to do is to disrupt this some of these structures. Then you learn how is the salt, the whole of the salt, when it's playing with with the water molecules. Now, as well, have a play with the CO2 injection in terms of also think in terms of CO2 sequestration, and to use the CO2 as a fluid for displacement of the oil. And here's something very interesting from the physics point of view, because your phase diagram that you know for the bulk phase really does not work when you are going for the confinement system. And with molecular dynamics, you actually can monitor what is going on and to distinguish between the fluid, the liquid phase, the gas, supercritical, for a given situation. Here is 200 nanometers with a 4 nanometers diameter that you would have it in your nanopores media. So you can learn the thermodynamics that usually in the nanoscale is changing with respect to those systems. Now, just I don't know how much time you still have it. So then let me just tell you what you can do further, not only for the oil and gas, directly to the oil and gas industry in terms of nano-EOR or nano-IOR, but also with this first principle calculations, you are able to design materials from scratch, mainly. So because since you are using quantum mechanics in order to describe the interaction of those systems, and you have played that with two situations that also is interesting in terms of the materials science for batteries and thermoelectric materials in terms of storage and conversion. The first one is you have used the molybdenum disulfide nanostructures in order to see how good is a lithium-ion battery. So with these calculations, you are able to see how is the activation energy with respect to the voltage. So this is quite amazing because you can predict the voltage of a material even if this material has not existed yet. So then you can propose ways to synthesize it or to see if it is interesting or not. The second one is related to the thermoelectrics, where one way to thermoelectric is mainly a material that you can convert heat in electricity. And then one way to characterize those materials is so-called the figure of merit, that you also are able to calculate by first principle calculations. And then you can predict that this was material that has been suggested for us from scratch, where you can mainly try to see what is going on in terms of the properties of those materials to see if it was an interesting one. In this particular case, some experimental people is trying to synthesize it based on these first principle calculations. And finally, as well, you can use those tools in order to think what to do with the CO2. Because one way is either to use the CO2 in another feedstock, and for that, you need to understand in terms of catalysis and the barriers for going from one system to the others. How is the energy reaction that you have during this process? And you are using actually nanostructures in order to, as a catalyzer, to tune to transform CO2 either in methane or formic acid. At the same time, the same nanostructures of molybdenum sulfide can be used for water splitting. That is something that you are able to predict by first principle calculations. So in a summary, so this is the idea is to try to use nanostructure. I mean, to think in terms of nano-EOR or nano-IOR, using nanostructures, or try to understand what is going on at the nanoscale of those systems. At the same time, these tools can also be helpful in order to predict some materials properties. And the interest point here is to do it in a controllable way. That is what I'll try to do it. So as a summary, I think I have to take as Feynman says, so Feynman spent some time here in CBPF. There are very nice chapters in his biography about that. And I think you should say that there are plenty of room still in the ground. So I think there are a lot of things to do at the nano scale, particularly think in terms of the nano oil and gas. So I have presented to you an integrated multi-scale approach from bottom up and also in terms of the top and down. The important point here is to try to understand what is going on at the molecular level, the phenomena that you have at the nanoscale. Sometimes experimentally it's difficult to understand the mechanism that you have there. Here it can be helpful. And as well as a cost-effective way to explore nanostructures under the controlled. So because you know what models and what systems you are putting there in a very realistic way, in the sense of this is under high temperature, high pressure, high salinity, in the operational conditions that you have, for instance, the micro porosity, the porous topology or the geometry of these pores. And as well, we think in terms of material design over a broad portfolio of energy and also infrastructure technology, because you can play, you try to understand what is going on these materials at a nanoscale. Now, I have to thank the people at our group, So those are the ones that has been involved on the work that I have showed to you. And also have to thank some of the agencies, and particularly the Petrobras on this project. And I also have to thank the opportunity to collaborate and also to interact with the people in Norway. I think this is, it has been said before, it is really a beginning. There are several things to do it. This nano technology applied to oil and gas industry is something that somehow you are at the edge of in terms of technologies. It would be very nice if we can continue this collaboration. And I would like to thank you for your attention. Thank you very much.
Okay, I think we are getting a bit short on time, so we move on. Next speaker is Lorival Flor from Golden Technologies.
Culture is innovation, technology, technical support for our customers in all the world, training courses and professional assistance, and environmental sustainability. Here, a little bit about Golden Technology. It's our plant production in outside of São Paulo, like this. And here it's our lab in São José dos Campos, close to Technical Park in São José. It's not important. Here, social responsibility also. Here, building innovation and technology. So over 25 our staff is involved with research and development. Over the 50% of our staff is committed to customer service attendance. And over 50 of associated with university degree or higher. We have a lot of cooperation with universities in all the world. Here we have this Cornell Institute Fiber and Fashion Innovation. It's a university from United States, Ithaca. We are a founding member of this institute in US. Here, some universities that we collaborate. I'm here because I believe in a strong collaboration between academia and the industry. We try to make the bridge between academia and industry. Of course, there are a lot of technologies inside the academia, but how is possible to transform this technology in products, in marketing? This is our purpose, to build this bridge between academia and the industry. Here, some partners that we work together. It's not important. A key technical support that we provide for our customers. We provide inside the customers. We provide by video conference. Here, technical support. And here, in Texter of Spain, we launched 3 books, technical books, not commercial books, but technical books. So, responsibility again. Okay. This is our company. I'm here, as I told you. It's very, very important to collaborate with universities. We supply technologies for many companies in the world. Nowadays, we supply for America, but for China, if you think, how is possible to export chemicals for China? If China is the country who produces the cheapest products or raw materials in the world, but we supply technologies, we supply new process, of course, with the chemicals. Thank you very much. As I told you, I want to spend your time here. Thank you very much.
Okay, the next talk is by Arne.
Okay. So, good afternoon. I'm Arne Skjeltorp, and I'm also thanking Jon Otto to invite me here to talk about in particular magnets used for tracer technology and for maybe removing pollutants. So I will be, this is sort of a picture soon coming in Norway. I put snow tires on my car just before I left coming here. And so I'm a founder of a company making magnets, and I will tell you a little bit about that. So the group or the company is situated just outside Oslo, in the southern part of Norway. And here again, we have here the Giamag location with offices and laboratories. We also have a nuclear reactor producing neutrons for materials research. So this is a reactor. This is the only reactor now in actually the Nordic countries where you can do materials research. In particular, we have a small angle neutron scattering facility where you can actually investigate nanoparticles. So this is a very special technique, well suited to investigate nanoparticles. Okay, so this is an outline of what I will be talking about. I will talk a little bit the challenges of actually pulling out nanoparticles from a solution. You can do it if you aggregate particles together in larger quantities, as Araki talking about. We have then actually worked on to make a special designed magnet to be able to pull out nanoparticles. The separation of particles or micrometer size is very is not difficult. So here is we show 4.5 micrometer particles, and you saw it was fairly quick. You can take a look once more. So that's dispersed in. So that happens in a few seconds. This is with our strong magnets. I will come back to you. So with nanoparticles, it would have not been so fast at all. With an ordinary magnet before the GMAG, it wouldn't have been possible with the low dispersion. So the new magnet design was required to extract nanometer-sized magnetic particles. And these nanoparticles, which was talked about before, are monodomain. So they don't break up into several domains. And they are really very small, and they move around very fast because of Brownian motion. So I just want to tell you a little bit about the force on a magnetic particle. This looks a little bit complicated, but the most important part is that if you have a particle, the force you need to be able to pull it is proportional to the magnetic field times the gradient, the variation of the magnetic field. That's very important. If you have a very high strength, it doesn't help. It's like a table. A high table with a ball on it, it won't roll. But if you tilt the table, it will roll. The steeper the slope, the faster it will roll. So it's exactly the same type of thing here. You cannot do very much with a B. The neodymium iron boron magnets you got now is pretty good. So what you can do something with is a variation in the magnetic field. So this is also a little bit complicated, but the force goes like this. The thermal motion, the smaller the particles, the faster they move. So it goes as 1 over r. If you have the magnetic force equal to the thermal force, you will see that you need a gradient here, which goes as 1 over the 4th power of the radius. That's quite scary, because if you go from 1 micrometer to 100 nanometers, you need 10,000 times larger gradient to be able to pull out the particle. That's for single particles. But if you have a high concentration, you get aggregation, then you get, of course, high moment, and you don't need this. So we claim that the magnets prior to this GMAG was not strong enough to be able to do that. So I now will talk about this new patented magnet. And that's led to this company, GMAG Technologies. And you can take a look at the website to get more information. So I want now to run a cartoon. The principle of magnet, this is very, very simple cartoon about it, so you have to take it as it goes. Yeah, it's actually sound to this one, but oop, it doesn't move. Okay. Okay. I have the sound here, but you don't hear it. So this is a magnet. Oop, oop. And the magnetic field coming out. So there's a south-north pole. And then you can have another magnet coming in with the opposite polage. So then you have a magnetic field going from this to this. So you get a higher concentration of magnetic flux. And you put them together. And then you put something called a yoke on the bottom. That's a special type of steel, low carbon steel. So and then some plates on the top, masks on the top with a special material. And the magnetic field comes out from a slit here. So it's very high concentration in a small region. And that's create this delta B, this gradient in the magnetic field. So that's a GMAG. Here is just a sketch of it. It's a lot of text around. You don't have to look at all the text, but it's actually a magnetic bottle. So the field is sort of trapped here. It goes from here to there and up there, and then it sort of goes around here, and then the magnetic field leaks out through the slit, creating this very high gradient. So we are able to get a B times delta B or gradient B of 1,000 tetra squared per meter. We think that's about 10 times at least higher than a commercial magnet. This is the first magnet we made, just absolutely the first one. And you see that was exactly what you saw. This is a magnetic field down here, up there, this shunting yoke, and then you have this mask on the top, and you have the magnetic field coming out. So far we have patents of this in Korea. USA was approved this summer, actually, Japan, Canada, EU. And we have various designs of this. So here is a circular magnet. Somebody is... So that's, well, put it here. So here's a circular geometry. You see the slit here. We can do the simulation, so we see the field variation around. So we have been making various designs of the fields. Here you have many, many slits optimized for nanoparticle separation in microfluidics, for example. And here is a circular disk type GMAG. So we are looking at this now just very simple experiment by catching nanoparticles. And here is a very primitive setup. You have a peristaltic pump here with a volume of very dilute magnetic nanoparticles coming across the magnet. And here is from the top. You might be able to see there's some brown spots here. So yeah, at the end. So here the particles are caught. So nothing comes out. All the magnetic nanoparticles of about, I guess, 50 nanometers are actually caught. So that's very important in tracer technology, or tracer usage, because then you have these magnetic nanoparticles spread over an enormous volume. So you just have a nanoparticle coming once in a while. So you really have to catch each particle as it comes out from the production valves. So we have the lab set actually where we have been able to verify this. So we are working out various design and the geometries, and also we're testing out different materials of the mask and so on. So it's in the stage of optimizing. We had V3 from Golden, from Araki's group, and me. We formed a group to be able to get a project in this FINEP Research Council Norway call, which was just announced 2 days ago. Unfortunately, we didn't get the project this time, but we think had a very good project, and it was just actually double, just both to do something with a nanotracer and also to remove pollutants in the textile industry. And I agree that this would be very relevant also in the oil sector, because you have local spills and so on. So we have actually been able to use these magnets to remove small oil droplets in water after you have separated water and oil, because then you get sort of micrometer-sized oil droplets with high charge, and you can't get them together to coalesce. Okay, that's sort of the write-up of what we wanted to use. New softwares, made by Araki, and our magnet. And we should test these setups both in Brazil and in Norway, and we do it. Okay, so here's partners, Gemag, Golden, and subcontractors, Professor Araki, and IFE, the Institute with the Tracer Department. You heard Tor Bjørnstad gave the presentation on this earlier presentation. He's an expert on this, and the University of Oslo we should also have included, and NTNU with Fossum. So here is just the principle. So first of all, Professor Araki makes the particles in all kind of shapes and functionalities. And so it could be either for tracers or for adsorption of pollutants, as he showed. So the point is you have to catch and separate the magnetic nanoparticles as it flow through something. And we have the magnet, so the miracle happens here. So it's just a principle. We have been able to do this in a laboratory scale already. Actually, both of these. And we had a setup at our institute. So GMAG, we have a contact with the tracer department, and they have two companies in Norway, Restrack and Resman. They are sort of one of the world leaders in tracer technology, and they have also a tracer club with the Conoco, Philips, Lundin, and Aramco, and so forth. And we had also this contact with the units. So we have a very good setup on the Norwegian side. And here just shows some measurements already of nanoparticle centers by Professor Araki. Here is a small angle neutrons set up. So we set the sample here, you get a diffraction or a refraction up here. And here's the scattered neutrons. And the peak here shows that it's a correlation peak here at 0.07 inverse angstrom. So that corresponds to a diameter of 90 angstrom or 9 nanometer, which I think agrees well with your. Okay, so then I will just talk a few minutes. You know, I have 5 minutes? Fine, okay. I don't need it, but so I can show you some other fancy applications here. Actually, the original use of magnetic particles was for cancer treatment, in the 1980s. And here, as we heard, these beads can be then decorated with all kind of stuff, antibodies and so on. If you wanted to, stick to cells or cancer cells or pollutants or whatever. So actually, I worked with Professor Ugelstad when he sort of invented these particles in the 1980s, 85, and he was able to make super paramagnetic spheres. These are micropores. So inside the pores, he made actually magnetic nanoparticles. So the particles, although they are big, 4.5 micron, and normally they would be not monodomain superparamagnetic, but because of that the particles inside were just of this size, they were superparamagnetic. So I worked with him already at that time, and this is a cancer cell which has been, just sticking to these magnetic particles, and you can then use a magnetic field to pull them out. That was to clean the bone marrow. If you had cancer cells in the bone, that you took out the bone marrow, mixed in these particles, and put on a magnetic field and put the bone marrow back. So that's been refined now enormously. So these Dina beads were bought by Life Technologies, and now it's owned by Fisher, Thermo Fisher, a big company in the US. So this is just shows how fast we can pull out these nano particles. Here it's just a very simple setup with a laser, and you shine it through the sample, and then you measure the time it takes. So it's sort of 40 minutes. We are able to clean it out with a low concentration. We are also looking into microfluidics. That's a very interesting coming field for all kind of things. You're making bioreactors or microreactors, to look at processes and biological processes for sensors and so on. So this is a very, very simple principle. You send a fluid in here with a mixture of magnetic and non-magnetic particles, which can be stuck to various species, and you're able to separate down here non-magnetic and magnetic. So that will come more and more. So we are designing now magnets to fit sort of into setups in this microfluidic field. We also have to do other things to survive. As a saying goes, you sell the fruit and the berries you got. So we have actually been able to make brakes in roller skis on a test experimental stage, so we think it might work. And you can control the brake using Bluetooth, from your grip there, so you can have a soft sort of braking. And of course in Norway it's very important with the skiing also in summer. Yeah. Actually, there's one thing we did just a couple of weeks ago. We had a stand at the University of Oslo, cutting edge. It was a presentation of innovators and innovations and things we wanted to demonstrate the strength of the magnet. So we said, okay, we want to push two magnets against each other. Then of course they repel each other very much. If you have it wrong, they will stick together and you never get them apart again. But so we made two magnets coming together here in sort of they're sort of steered there, and then you have an arm there. So if you do that, you force these magnets down toward each other. So you need about 200 kilograms to push them together. And nobody were able to do it actually. And we sold this to an amusement park. There came somebody and wanted to, so we have sold this for 25,000 real or something like that. So this might be a big product. Yeah. Okay, so you're not already talked about that. So I have been arranging the Yale schools for many, many years. So here's actually the last one with the 78 participants from 22 countries and 21 from Brazil. That was a fantastic meeting, and here was the other one in Portugalinas. So we are preparing now. The next one will take place next year, and the title will be Physics Inspired by Living Matter. And it's been a very good school. So far, 5 of the lecturers have received the Nobel Prize. And the last one, Michael Kosterlitz got it now this last time. He lectured there in '81. So if you are invited as a lecturer to this school, the chance of obtaining the Nobel Prize is increasing enormously. So it's, yeah. Okay, so Jonathan also mentioned we are eagerly awaiting, whether we get some funding to continue this this great collaboration with Brazil. I think it's been extremely fruitful, and I really commend Jonathan for his 15-year work to to actually come here and to bring groups in Brazil and Norway together. It's been absolutely fantastic. So you deserve all the credit. We are just afraid that if you don't get these, it might be a sudden stop. So we hope. Anybody from the Research Council here? No.
That's great.
Yeah. Yeah. Bring people together. Thinking. Yeah, thinking, thinking happens when people meet and talk to each other.
Correct.
Yes, that's the gist of, innovation. Innovation in my head is success in the market. You have to remember that one, and that's a simple prescription. That's in our case. So we have this slogan: magnetize your innovation. So we are open for all kind of. Here are the sponsors, stakeholders, IFE Venture, Kjeller Innovation, also this county around Kjeller, and Research Council Norway and Innovation Norway. And here is a team. Me, Paul, he gave a talk. He's sitting there. So he is also, and Henrik Høyer, and this is our CEO. He's a young, very enthusiastic guy, and he has contacts with our other groups. Paul is also has been working with Sanofi in France, and also with the microfluidics laboratory in Paris. And I'm also working with energy technology. We have contacts now many places in the world. So we have a good network, and we see here in Brazil, here in Sao Paulo and Rio, and also in Recife, and also in Campinas. I follow Donato. So I will just stop with Mark Twain. He said, "The secret of getting ahead is getting started." Thank you.
Okay, we have to hurry up a bit because we have to finish, I think, before 6. Or, yeah, before the hour.
Yeah, you take this.
The next speaker is Ingebert Fjelde from Iris.
Yeah. Thank you for inviting me. If you were here in the beginning, you saw a list of the presenters, and I saw that my presentation was in red, so I'm red listed. Maybe because I will say something about oil-based mud. I'm not sure. Is there, there it is. So most of what I want to say is also related to other enhanced oil recovery methods. It's not only use of nanoparticles. But if you are asking the mud companies, you should not have any mud invasion in a rock. But in reality, you sometimes have a lot, and sometimes you have only a small amount. So first I will say something about how important it is to have representative conditions when you are preparing the rock that you will use in the lab. I will give you a few examples only of references to the literature where they have used nanoparticles for EOR. And then I will tell you something about the mud composition, which can be rather complex. And then show some examples of the effect of mud components, and also say something about possible interactions between the mud components and
components in the nanoparticle formulation. If you should estimate the potential for EOR, you should have the reference, the level estimate for the reference method. In the North Sea, usually water flooding is the reference method. So you should do better than water flooding. But I can tell you that there is a field in the North Sea, it's also published, it's the Gullfaks field, where they estimated that the residual oil saturation should be 30 to 35%. But after a while, they were not able to predict the production. They produced more than that should tell. So they, to tell a very long story, just in a short way, is that after a while they drilled observation wells and saw that the residual oil saturation was at least lower than 20%, in some places between 10 and 15%. So they have prepared rock samples in a wrong way, and they estimated also the effect of several effects in a wrong way. But when we are doing experiments, it's important to use the reservoir temperature and pressure, at least at the end. You should use reservoir fluids, formation water, and crude oil. And of course, the crude oil should not be contaminated by chemicals that had been added. For example, flow assurance chemicals. You should know the composition of the fluid that you should inject. And then you have the reservoir rock sample. Maybe you have at least a few, but that should represent your reservoir. And some people is then saying, I'm not doing anything with the reservoir rock sample that I have. But in reality, you have done something when you're taking it up. You're reducing the temperature and pressure. But in addition, you may have contaminations, say, of drilling fluids. There's a few examples of how nanoparticles have been studied for use in EOR. It has either been used only the particles, or they have added in a formulation to improve the properties. It has been published something on change in wettability, and also use of nanoparticles as a foaming agent. I forgot to say, if you have a wettability alteration, you want to accelerate the oil production. By foaming, using a foam, you can improve the volumetric sweep of a gas flood. Has been used, nanoparticles prepare the polymers for water diversion, and there are also some work on emulsions to improve the volumetric sweep. If we are looking at water-based mud, there's many components. It's a very complex mixture, and many of them is not single structure products. It's a range of chemical structures in the products. If you're looking here, you can see that we have bentonite clay. So there has been talking about clay earlier today. So that's added for rheology, but also filtration control. You can see that it's impure montmorillonite clay. So it's not very pure clay. There's also other components. You're adding barite as a weight material. And then I jump into, it's not working. You often have a polymer. There's different types of polymers that are used. In this case, it's a xanthane, it's a biopolymer. But polymers can be very difficult to remove from a porous media if it has entered. Then you have, in this case, it's potassium chloride brine. So you have rather high concentration of potassium chloride. It's a few percent at least. That's added to stabilize the formation. And then you're adding some components to optimize the pH and brine composition. So in this case, we had a reservoir rock sample. It's with a high permeability. We know that it was a potassium chloride mud. So you can see that we started, is this one working? We're starting here at 12,000 when we're starting to produce out of our rock samples. It's much higher than the formation water that we injected that was in the range 200 to 300 ppm. So some people are saying that we should not clean the rock. If you have not cleaned it, in this case, it has contained a lot of potassium. And I will show you later that that will affect the amount of oil that is absorbed on the reservoir rock. So it's clearly contaminated in this case. You can also in this case see that by scanning electron microscopy, we found clusters inside the rock of barite and clay. And in some cases also we saw the polymers string. So if you have invasion of particles or polymers, you have a formation damage. You're usually reducing the permeability. Other chemicals that is going in can change the wettability. But if you can see here there's a high concentration of barium. So in this case, the core plugs were drilled in that way that should be expected. So but the clay here, bentonite clay, is the surface area of the clay is very high. So it's changing the surface area inside the rock a lot if you have invasion. Just to show you an example here of the effect of the brine. In this case, we are looking at oil absorption. We found that it was lower with potassium chloride in the rock than formation water. You can see that we are injecting water to a saturated, brine-saturated rock, and we measure the polar concentration of polar components. And you can see that there's a delay in concentration of polar components here for the formation water. The one is the injected level. You can see for potassium chloride, it seems to be no delay at all. So it's affecting the absorption of polar components that is related then to the wettability. And we have seen that potassium chloride for some rock can have similar effect as low salinity water flooding. That is one EOR method that can sometimes be used to enhance the oil recovery. If we are looking at the bentonite clay, we found that it's rather oil wet. In this case, we have used the flotation method. But it was work done by a master student. We had different types of powders, and we sieved it. And you can see that bentonite clay is one of the most oil wet clay that we have. Zero is strongly water wet, and then the less and less water wet with increasing number here. So if we have an invasion of the bentonite clay, it seems that it will be oil wet, which means that we are changing with a contamination, we will get wettability conditions that is not representative. We also saw that when we injected low salinity water, that oil and water was produced, it was a stabilized emulsion when it was produced. So then to the oil-based mud. In this case, we have an organoclay. It's a modified bentonite clay, absorbed polar components on the clay surface to change the wettability, so it should be easier to disperse in the oil phase. But we also have barite, but in addition to that, we have emulsifiers. The secondary emulsifier is usually a strong wetting agent that should convert the wettability of cuttings to more oil wet. It's often the cheapest one. Then we have the primary emulsifier, because you should prepare an emulsion here. It's called oil-based mud, but most of them is continuous oil phase emulsion with water droplets. So then you can see we're also optimizing the brine concentration and pH in this case. So just, we did this in 2003-04, I think, but published later. But we had a flow cell, and we injected an emulsion prepared by all the components except the clay and barite. So you can see that started to destabilize in the flow cell. You can see the open area with oil phase. But when we added the organoclay, it was a stable emulsion. So how can we see if there is a contamination by oil-based mud? There's many components that it's difficult to analyze for, but we have the emulsifiers. So you can at least analyze for that. You see the interfacial tension between oil and, in this case, ductank oil is approximately 25 millinewton per meter. So we had one core that we did not expose to the mud filtrate. And then we used two types of mud filtrates from the oil-based mud. And you can see that the interfacial tension between the produced oil phase when we injected the stock tank oil, it was down to 4 to 5 millinewton per meter. And we injected long enough that the differential pressure across the core was stable. Then we stopped and analyzed the samples after. But you can see that we have not injected long enough, because you can see that there's still a slow release of the emulsifiers. So it should have been injected for a longer time. And when we did spontaneous imbibition experiments, we placed these core plugs in water, and due to capillary forces, the water was going in. We saw that spontaneous imbibition of the two cores exposed to mud filtrate was less than the reference core. So the exposure to the mud filtrate converted them to less water wet. And that can be a problem also in the reservoir if you have invasion and you're doing loggings, that the wettability can change in the near well region. So we have seen many types of nanoparticles today, but they interact different, and you can also have different types of muds. But of course, if you have invasion of brine, it can change the properties of the minerals, the charge of the surfaces. So when you're starting then if you are using a non-clean core plug, starting to inject a brine, you will get a cation exchange of the clay, and then you will change the composition of the water that you are injecting. So that can also, if you have to inject nanoparticles in, say, a low salinity brine. It's not necessarily low salinity when it's coming a certain distance from the well, because it will change due to also interaction with the rock itself, but also the contaminations. There may also be interaction between the mud particles, and you have the mud chemicals that can be released, say, from the organoclay that have polar components absorbed. You sometimes see that they are absorbed also from the organoclay, and then it can absorb on something else. That may be the nanoparticles. I've not said so much about the oil field, but of course it's important that you are able to transport the nanoparticles. In the field, there is often invasion of the mud close to the well. So if the concentration is not extremely low and you have extremely high retention, then it should be possible to transport it. If you have high retention of mud particles, then it can be a problem to transport it out in the reservoir. But the one thing that is important, I mentioned it just a short time ago, is that you always have an interaction between the injection fluid and the minerals that you have in the rock. So that can change the composition. So if you should design a system, it's important that it's you can have it in the injection brine, but also you can have it in still the same properties if the injection water composition has changed. So a summary, it's very important to have representative conditions. That's true for all EOR methods. And mud components with the potential to affect the flow conditions, the waterability, and also the transport of nanoparticles, they should ideally be removed. Or if not, you should at least have some knowledge about the effect it can have on your system. Yes. Thank you.
Okay, that was the last talk. Are there any questions to any of the speakers from anybody? We are not supposed, actually we have 5 minutes for to finish this before the room is going to be occupied, I think. So we are supposed to do a wrap-up. I'm doing the wrap-up now. I've done the wrap-up, I think. This is okay. And then we are supposed to have matchmaking for new project proposals and partnership. Is there anybody who wants to matchmake? Okay. 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 So we have. Okay. Good. Fantastic. So thank you. I think we are. There is a coffee outside.
Black milk. Oh, yes, sir. I will send you.
Okay, then we have come to the last moment at this conference, the fourth November conference, and we will have a small panel discussion. So I can Morten, Dan, and Professor Carvalho, and Jon Kreppe just come to the stage. But before we start the panel discussions, I will just ask the sessions leader make some summary up and key findings from each of the sessions. So who want to be first? Anis, take the word. Oh yeah, you have prepared something as well.
So I've been sharing the session on multi-phase flow assurance, and I think it was quite an interesting session where we tried to combine contributions from universities. As you see, the three first talks, PUC, UEU collaboration. We actually have received funding from the Utforsk program, so we elaborated on how we will use the money in terms of further education of students. And also Professor Daniel Rodriguez talked about the theoretical, numerical advances in modeling multi-phase flows, and how the need of experimental controlled experiments are important. So this was the scientific aspect. Then we had a very refreshing talk from João Carneiro from Sintef, who sort of had the language to bridge the scientific talks into industrial applications, and also highlights the importance of basic and controlled research. And Kjell-Arne, you updated us on the new Sintef flow loop and the new experiments that are going to take place. And you formally invited us to take a look at this campaign. And we had also two very interesting talks from ESSS, which is a software company, and Petrobras, or a guy with long experience from Petrobras. And I think the main takeout from me, coming from academia, is that we're actually on the right path in terms of these fundamental researches are still something that are needed in the big scale industrial applications. So I think this is my main takeaway from the session.
Thank you. Steinar?
Is my presentation there too? No, it's not a presentation, but I thought I'd try to do it in a similar manner as you do. So we had the other morning session about environmental monitoring and risk mitigation, and also there were different kinds of issues. The first 2 or 3 there was about this application that we filed with BN21 this time in the first call. And it was about exploring novel DNA-based solutions for doing environmental monitoring. And it's a kind of a very interesting topic seen from the industry side, and also from the scientific community. It's really a hot topic. It didn't get funded this time, but we discussed it, and we gained also interest from the industry people in the audience also. So our conclusion is that we want to pursue this further and think and see what kind of opportunities we will have further on this. So that was the first. Then we wanted, and then it was also about what we presented last year, was about corals in deep sea and monitor of coral in deep sea. That is still a hot issue that we will also try. It wasn't possible to apply for anything like that in this call because of this SME constraint. And maybe if things go differently now, the industry is very ready to join on that. So this is also another thing we will continue or reconsider for that. And then we were introducing or letting the floor open or having the session open for new ideas. 2 different ideas, one from Norway, one from Brazil. From Norway, we had issues related to treatment of oil-based mud. This wasn't an issue in Norway before quite recently, but has become a very, very hot issue where the oil industry is very interested, are engaging in it. And it is maybe an issue that will come up here in Brazil as well. Couldn't get any clear answer on that, but at least encouraged to try to pick up and follow up on that. In that case, we have something to work on together. And the final topic was about biotechnology solutions for metal removal from pre-salt oil. And this is also from this BioBureau company here in Rio, a biotechnology company. And then we had a discussion about biotechnology in general, related to oil and gas. And through that discussion, we kind of, we came to some ideas about that the environmental monitoring methods that we are talking about in the drill cuttings talk, and this biotechnology solutions approaches that they have here is actually very well suited for EOR. And so we were thinking that next year we would like to make a combined EOR and environment session and biotechnology session. Was that right, Ying? Yeah, thank you. Okay, thank you.
Yes. Jon or Bjarne, who want to be next? Bjarne.
Yeah, okay, so I chaired the session on integrated operations together with Kazuo Nishimoto. He had to leave, okay, yeah. So I mean, integration today, that's not a new thing. Every solution more or less has some kind of integration. So the question is more about how deep is the integration, how many different aspects do you actually integrate, and it's also a question of if you integrate a lot, things inevitably gets more complex. So there also has to be a trade-off in terms of added complexity and cost versus benefits. So we had 5 talks in addition to an introduction on different aspects of integration. Petrobras had a nice talk on the integration between people and technology in the setting where you have to, of course, the technology as such is not enough. You have to include the work flows and the work environment as such. So we had a nice concrete presentation on this. Then we had a presentation from Alberto Santos from Unicamp on the decision processes related to reservoir management. That is, as you are producing over years, tens of years, several decades, you need a way of collecting the data, updating your models, using your models for decision support. And there's a structured way, and they developed a certain procedure for actually achieving this based on the 12-step activities. Then there was a talk by Morten Dahlen from the University of Oslo. And one thing I thought was quite interesting there was the following. In Norway, we have several centers. Centers for research-based innovations, centers for environmental friendly technologies. And what they had done was that they had, and these centers are usually quite autonomous. So what they had done in Oslo was to look at the borders between centers and developing new activities based on this. And this was in a big data setting. So I thought this was quite interesting. And that's probably something several others could use as a kind of a role model or a way of thinking. How can you benefit on the borderlines between already strong centers? Yeah, and then there was a nice talk from Petrobras again on integrated operations related to telemedicine, which has to do with the fact that you have someone somewhere, you do not have access to all the medical expertise you need. You may have a nurse available, and then making this expertise available fast was a kind of 3 to 5 minute response time, and in particular the application is offshore platforms. So you have some person, and you can then and you have a nurse, and you have a setting, and you have access to specialists at the hospital, and then you can derive a much more precise diagnosis. In particular, do you need to transport this person onshore or not? And finally, there was a nice presentation by Kjell Arne on a concept developed by SINTEF over many years related to what is called a smart pipe concept, where you have a pipe with, in a sense, embedded sensors and communication system, so that you have an online monitoring system, so which may, for instance, remove the need for inspections. So, and it was a nice session. We had quite a lot of discussions, so I guess that's a wrapping up of that session. Thanks.
Then Professor Jon Ole Otto Fossum.
Okay, so I was sort of heading the session on which is called nanotechnology for IOR and UR. So this session actually had 7 talks. 7 talks. It had a good attendance, I would say. It covered basic mechanisms and applications. It had talks both from academic and non-academic people. Basically all the talks touched upon natural or functionalized nanoparticles for the purpose of EOR, IOR, tracer technology, or advanced materials processing of energy materials was also touched upon. So the natural materials, natural nanoparticles that people talked about were mainly clays. The talks also covered synthesis, experiments, and numerical work. And there was a very interesting talk by Arne, of course, about magnetic capturing, Arne Skjeltorp, about a new way of capturing tracer particles by high gradient magnetic fields. One thing that I mentioned, of course, was that we have had a very successful, over 14 years now, nanotech network working in Brazil and Norway. We have produced lots of publications, more than 30, more than 150 conference proceedings, etc. And exchanged many people. So we would like to continue this. And in order to do that, we need funding, because now our funding is ending in December, and next year we have nothing. So we have an INPART application in, and we have a Petromax 2 application in the system. And the latter one is actually about what this session was about, which is tracer technology and EOR. So I encouraged the Research Council to give us some money. So there were two INPART actually projects that were mentioned in this session. That is the one that goes on this nanotech network, and the other one from IRIS and Ying. Okay, thank you.
Okay, then I had got three gentlemen here now in the panel just to make some reflections about the journey we had so far together in this collaboration, and maybe look ahead. And I think I just start with Professor Corallo.
I think it's these. Well, you have to be very, very close to make them. Working. Okay, so my reflection is that this is the third conference of this type that I attend. And I think it's clear there is a synergy. There are a lot of collaboration already going on. It started in an informal way of contact of different researchers from academia and companies. I think it's maturing. It's becoming more clear, the synergy and the possible collaboration. This is, at least in my area of field, this is very clear how this type of environment bring people together and bring new ideas. So I think the one challenge that I see, and I think it's would be a great step, is taking the research from the fundamental all the way to application. So it's good to see different types of companies, not only oil production companies, but service companies, because so I think that's a way of bringing all these players together and going from the very fundamental research to technology development and application. So it would be very nice to see this growing in very large type projects that would have all these different players with all the different steps of development.
Yes, just pass it on to Jon. Okay, thank you. So I have been with this group since the beginning in 2013, I think, and it has grown to be, to me, a very important meeting place. And we have closer, and we have different levels of participation and presentations, and both on the detailed research. I attended the IOR, which was really basic research, you know, and then we have the general sessions with all these government bodies present and decision makers and so on. So, and I've always been a big promoter of collaboration between academia and the industry. And in this place, we have been able to attract both sides, have presentations from both sides, and we can create new ideas, I think, and get inspired by each other. So hopefully we can continue, and I think somehow we need to get it financed. And I don't know how. Of course, we have the import application that you, Kjell, are heading up, crossing our fingers. I guess the decision is on November 15th, I think. Yeah. So we'll see. But in addition to that, I think for professors and PhD students in both sides, in order to have close collaboration that will benefit both parties, including the host universities, we need to have double degrees, I think. We have to develop the double degree system. And we do have double degrees established at NTNU with some universities around the world, and it's not very complicated because each university can have different requirements in terms of courses and so on, but then we have the same requirement for the PhD thesis or dissertation. So if we can agree on that and get things like that financed, then we have a good mechanism for getting more collaboration, concrete collaboration, not just meeting once a year, but actually get results that benefit both parties. So let's try to do that. Thank you.
I think this is... First, I will start by thanking the local organizers for the job they have done to setting up this conference. I think this is the best conference of the four I've attended. I've attended all four conferences, and it has improved every year. We have been more and more concrete in what we are talking about. There has been a lot of collaborations started in this meeting, and it still continues. And I think we should build on the strength that we have achieved over these 4 years, and I am convinced that we will come back next year for the November conference 2017. For those of you who listened to me yesterday, I think we should broaden the energy spectrum a little, not necessarily move all the way to take all important aspects of energy, but from my perspective and from the University of Oslo, we would like to see something on energy systems and renewables, because we believe that the oil and gas industry will be an important player in the green transition in the years to come. So that's something we would like to see here, and Brazil has a huge potential when it comes to renewables. It's already a country with a lot of renewable energy, and I think that is as an important next step if you're going to pick up other topics. The other thing that we can improve on is student exchange, not necessarily on the PhD, also on the PhD level, but also on master and bachelor level. And making some structured exchange programs, that is something that we are looking forward to see. We have a few, we have students coming here, all universities in Norway, and I think that we can improve these exchange programs, making them more dedicated by setting up the right courses in the right semesters and so on. So I think there is a huge potential going on, and on behalf of the University of Oslo, I can promise you that we will be around collaborating with the Brazilian colleagues for many, many years. And when it comes to this Norwegian network, we have been research institutes and universities, and just before I went here, the University of Bergen knocked on the door and said that they will be a part of the network for the years to come. And we know that they have interesting projects also in the oil and gas domain, in structural geology and basin modeling and so on. So I think this is something that has come, and it will stay as an arena for us to collaborate in for many, many years, and I'm really looking forward to that. So thank you.
Okay, this is a panel discussion, and I actually, is there anything from the audience that you would like to ask? I mean, now you have the opportunity. I mean, we have not got, 100% promises over a new BN21 call, but we're working on it, so we expect it, and I think that is very important to move forward. I mean, last year it was announced, It was a little bit disappointment that it was not headed against institution. No, it most likely will be. So that is as a good signal. How important is this joint calls from your Carvalho?
I think they are very important. I think it funds the collaboration. There have been mechanism already in place before, like copies, SIU type agreement, and I particularly had like a Science Without Border project with Norwegian partners. But so I think these joint calls are very important for student exchange and actually doing the research, funding the actual research of equipment and consumables and things like that. So I think they're very important.
Yeah, I can completely agree with you on that. And of course, there are mechanisms, funding mechanisms in each of the countries also that we can use. But the joint calls are extremely important.
Yeah, it's the same for me. These joint calls are important, and what we could see more of, I think, is the joint calls where we can hire groups of PhD students in both sides, not only one here and one there, but also make these clusters of students that can work together over, let's say, 4 years. That I think is an important thing to do, and it will be. And I know it's difficult, but having a group of, let's say, 3 to 4 supervisors in both in Norway and in Brazil, and 5 to 6 PhD students working together over a period of 4 years. Having calls like that will be very nice, and those has to be joint in some way or another. And I think that will lift the research to another level, at least seen from a university side.
Okay, I don't think we are going to push it very much more. No, this positive signals. I mean, the joint calls is very important. And personally, I feel that it was said here in the beginning. I don't remember who it was, that the November conference has become a tradition. And when something is a tradition, it's usually something positive with it. That's at least my impression. And I feel that now for each year, this is more like a reunion than new faces. So personally, I really appreciate coming here to meet you guys every year. Is there anyone in the audience that would like to say something? Energy is out. I think then I just will just summarize and say that we are coming to an end to this conference. We have had many good discussions. We have identified several points that could be developed into a new BN21 application. I think in all sessions I have just followed 2 of them because I have been on stage and the others. So that is positive. We are looking forward to the call in near future. And I think by that, I will really say thank you for the engagement from the General Consulate, from the Research Council, from the Norwegian Ministry, and FINEP and ANP. I don't think they are here now. And Innovation Norway, of course. Jostein Gunnar for excellent leading us through 1.5 days. So I'm in the collaboration that we are taking care of the scientific program, and that you are organizing and taking the fund is very good. So this has become now a very good work sharing, and especially Rune that has been instrumental here in Brazil to make all the contacts and create a very good program, I think, on day 1. So with those words, I think I hope I... Yes, of course, our host here, which has this difficult... I think, of course, we want to say thank you to our host. And it was said earlier yesterday that we feel more home here, maybe, than in a hotel. So maybe that this is something that we will repeat. Not necessarily here, but I think this is a nice exercise, and we will find good solutions on that. So with those words, thank you very much for your engagement. Thank you for your preparations and presentations. And I wish you all a good journey home for those who's traveling home. Tomorrow here is a day off for the Brazilians, so I guess many of you are eager to get home. So thank you very much.
Norge.